We're hoping to launch our satellite in early 2025. The goal of this semester is to build an entire satellite over the course of 2 semesters and launch it. So these are small research satellites that go into low Earth orbit. Our mission in particular is to use a bunch of cameras to do orbit detection. So we'll take a bunch of photos of the Earth, do landmark detection with a machine learning algorithm, and from there we can estimate our orbit. So right now one of the biggest problems in space is that GPS is highly regulated in low Earth orbit and very expensive. We're trying to find a cheaper, more efficient way of finding your orbit in space. We have 6 cameras on board, 1 facing in each direction, and these are going to feed into our Jetson Nano, which is a small GPU module, lightweight, which we'll run our machine learning model on in order to do our estimation.
These are the 2 components that the comms team works with the most. Is we have the antenna, which is made out of a tape measure. It has rigidity, but you can also fold it down. The satellite has to deploy completely like in a cube shape, but once you get into orbit, you want an antenna.
So everything in the aerospace industry, I'm striving to be a part of. When I heard about the opportunity in this class to actually design a satellite, I jumped right to it. Anytime I can touch actual flight hardware, it's always a great opportunity. So we started prototyping individual small parts of the design very early on with 3D printed components. And then that slowly moved to more real hardware as avionics gave us boards. We were building this as we were designing at the same time because that revealed a lot of design flaws and iterations that needed to be done. We've taken off the exterior board so you can see the inside. Here is more of the exterior and what's also going to be our deployable model here. So we're going to do a burn wire and the deployed solar panels will actually come out. And that's what this is a deployed state showing. So they're going to flip open at 135 degrees.
When I first met Zach, I joined his lab and then I heard about this class. And was really excited about the chance to actually start something from the very beginning, even though I knew nothing about it, and then get this far. Yeah, so it was kind of cool to be able to start from scratch. We literally walked in the first day of class and had nothing, and it was let's build a CubeSat. And it's taught me a lot about actual how we design, how we iterate, because it's all been done so fast. This board system is what's activating the burn wire to actually burn this. So we'll be sending the commands through the computer to the main board, to the battery board, and then we'll heat up this nichrome wire. And when we heat up the wire, it will melt the fishing line that should deploy the panels. The actual model is going to have burn wires in different locations, and we'll be running different circuits at the same time so we can tie these tighter. And so these boards will be in the satellite and we'll all be sending basically automated commands on a timer. So it will come out of the dispenser box, start a timer, and after 45 minutes, these burn wire circuits will initiate to actually deploy. And this angle is strategic. We are using a block there to make sure that it doesn't deploy past that. But really the beauty of this design is kind of the simplicity, right? So there's no locking hinges we have to worry about. There's no tiny hinge failure points. We're literally leveraging the fact that a tape measure will spring back to its original position to do this.
So as you can see right now, the satellite is actually tumbling at a really rapid rate. And essentially what we do is some kind of a control which starts detumbling the satellite. So it's essentially using magneto-torque coils. So that interacts with the Earth's magnetic field and produces a torque which controls the force on the satellite itself and makes it detumble. And as you can see from the rapid rate at which it was tumbling before, it's reduced to a much slower rate. And this is going to happen over a span of 2 hours. We're basically testing out a control algorithm using the simulator that we've developed. Similarly, we also have estimation algorithms built in, which are going to determine what is the attitude of the satellite itself and also what is the position of the satellite in orbit. So you can see that the attitude that you're coming is exactly the same, which is what we want. We looked at multiple cameras for determining what could be the best for our system, which is small and compact, but yet is able to capture stars and be able to function as a star tracker and give us the attitude that we need.
We're the vision team, and what our responsibility is essentially to take images captured by the cameras on the satellite and kind of run that through a learning pipeline that eventually helps determine the position of the satellite. This would be one of the cameras that's on the satellite. We have 6, and at any point some of them would be pointing towards the Earth. So what we do is we basically high level take those images of the Earth. We first run it through a region classifier that basically just determines what region of the Earth we're looking at. Depending on what regions we think we're roughly looking at, we pass that off to landmark detection models that we've trained to essentially detect landmarks in each region. Landmarks being features, for example, like points along the coast that help us pinpoint the exact longitude and latitude.
Each data point in this frame, we need to know the altitude and the actual location of this pixel point in the image. At the end of the process stage, the pipeline, we need to multiply the pixel value in the image by the projection matrix, which is what we will achieve and get by doing the camera calibration things.
Welcome to the anechoic chamber. In this chamber, we wanted to measure the radiation pattern of the antenna when attached to the satellite.
Oh, we're a DIY kind of situation here. This is good.